at the Cassandra Summit Europe 2013. The aim of our project PNS 3.0 was to replace relational databases used by our application PNS by Cassandra. And during this presentation at the Cassandra Summit Europe, I explain why we choose Cassandra for our application PNS, how we did the migration of the PNS data from relational databases to Cassandra without any interruption of service, and the new behavior of our application PNS after the migration to Cassandra. The short story now, we have a linear scalability for our application, we have a robust database, and we have also very low response time, so very good performances. Today, I would like to give you once again a very short description of our application PNS, and then to highlight on two new components we added to our platform during the last months. The first one is caring, and it's mainly here a question of design. I would like here to explain why we designed the feature, the management of the identifiers of our customers with graphs with Cassandra. And the other component is about analytics. And here I would like to explain how we have installed Hadoop Hive with Cassandra in such a way that now we can run analytic queries without any impact in our online queries. So a very short description of our application PNS at first. PNS is a highly available service for collecting and serving live data about the Orange customers. We store a few hundreds of properties for each customer in our database. And because the users of this application are the Orange customers themselves when they are logged to the Orange portal or the sellers in the Orange shops, we need a very high availability and low latency. Here is a big picture of our application. So on the bottom left of this picture, you can see many data providers who send every day many files to our platform. And as soon as we receive those files, we inject the data in the PNS database. And on the top left, you can see a lot of users who send a lot of HTTP requests for querying or updating the data. We have daily peaks at 15,000 of queries per second. Those queries are received in web servers. The web servers send the query to the database and return the result to the PNS users. Because we need a very high availability, our architecture is based on two data centers. The first one is in Bagnolet near Paris, and the second one is in Sophia Antipolis in the French Riviera. We are using two web services. The first one is written in C++ and the second one in PHP. And we use also Python modules for injection of data that we receive from our data providers. A few key dates about our project PNS 3.0 and mainly about the season 2. The season 1 was the migration of most of the features from relational database to Cassandra, and we did the migration of the simplest features, and the season 2 was the less simple, the more complex. So there were two components. The first one is caring, and it's about the management of the identifiers of our customer. And the second one is for analytics, it is the installation of Hadoop Hive. So now I'm going to focus on the caring component. And mainly here, I would like to explain why we choose a design with graph with Cassandra. At the end of the last year, we had nearly 35 tables in our PNS database, in our Cassandra database. All those tables have a primary key, which is a customer ID, and of course, many other columns. So when we want to retrieve some information about a customer, it's very easy to do with a query such as select column 1, column 2 from customers, where customer ID equals the value of the identifier. But here, in this case, what is really a customer ID? At Orange, we are using many kinds of identifiers for our customer. Sometimes we use their cell number as identifier. Sometimes we use their internet account. Sometimes we use their email address. Sometimes we use other things, for example, an IAC, which is an identifier used by some Orange applications. And we have also many other kinds of identifiers. And for many reasons, the data is stored in tables having different primary keys, having different identifiers of customers. An example is that there are some data which are often retrieved using a cell number. So in this case, we try as much as possible to store those data in table where the primary key is a cell number. But all our customers don't have a cell number, so it's not possible to store all the data in such tables. So sometimes we have to store the data in tables where the primary key is not a cell number. And there are many other reasons why we have different primary keys. When a user wants to retrieve some information about a customer, usually he knows one and only one customer identifier. For example, he may know the cell number of the customer. And when we want to retrieve this information, so he provides the cell number in his HTTP request. And when we want to retrieve this information in the database, unfortunately, this information is stored in a table having a different primary key, a different kind of identifier. So in this case, we have to translate the identifier provided by the users into the identifier used as primary key in our table. When we were using relational databases, we were managing the identifiers of our customers in one table where the primary key is the IAC. IAC is a kind of identifier. And there was one column for each kind of identifier. One column for the cell number, one column for the email address, one column for the internet account, and so on. And there was one secondary index built on each of those columns. So it was very easy to translate, for example, a cell number into an email address with a query such as select email address from customers where cell number equals the value of the cell number. But this design, as you can see, requires a lot of secondary indexes, and those secondary indexes have very high cardinality because a cell number is owned by one and only one customer, but the same for the email address and so on. And it is not the best use case for Cassandra, this kind of secondary indexes. But that's the reason why we don't want to use this design with Cassandra, and we try to find another kind of design. If we look at the identifiers of one customer, we can see that we can draw them with a graph. Here is an example of a customer having 4 identifiers: an email address, a cell number, an internet account, and an IAC. And as you can see, we can draw them with a graph with 4 vertices, and of course edges between the vertices. So if we are able to explore this graph, we are able to translate a customer ID into another kind of customer ID of the same customer. What is interesting here also is that we could imagine that this customer is married. His wife has also her own identifiers. She has her own email address. She has her own cell number. She has her own IAC. Probably she uses the same internet account because in a family, usually everybody use the same internet account. So we can draw all these identifiers with a graph. Maybe they have a child or many children, and the child also has his own cell number, his own email address, or maybe many email addresses. He has his own IAC, and probably he uses the same internet account as his parents. So when a user wants to retrieve some information of a customer and knows the email address, and this the information that the users want to retrieve is stored in a table where the primary key is the cell number. We just have to explore the graph, and then we are able to retrieve the cell number and then to query the information required by the user. It could be also the opposite. The users know the cell number and wants to retrieve information which is indexed by an email address. So what we want to do is to explore the graph in all the directions. We have created a table for storing the edges between the identifiers. For each identifier, we have two informations: the type of the identifier, for example, an email address, a cell number, or an internet account, and the value of this identifier, the cell number or the email address. So we have a primary key, the compound key, made of 4 columns. The type and the value of the initial identifier of the edge, and the type and the value of the initial identifier, of the final identifier of the edge. We have added a column of type map, that we use for storing any kind of information which is relevant for the graph exploration. The partitioning key of this table is the value of the initial identifier. So when we execute a query such as select star from graph where ID value 1 in the value of an identifier, we are able to retrieve all the neighbors of this identifier in the graph. We have nearly 500 million of edges in this graph. And this graph, as you have seen, is not just a single large graph, but it's rather a lot of small independent graphs where each vertex has very few neighbors. So the search of a customer ID is limited into a small subset of edges and vertices. Because we need to explore the graph in all the directions, for each edge, we need to store 2 rows in our table, one for both directions. So each time we want to insert, update, or delete an edge in our graph, we need to insert, update, or delete 2 rows in the table. And for that, we use the atomic batch mode of Cassandra. We don't want to calculate online the shortest path between the edges because we can predefine them and pre-configure them in our application in advance. Obviously, we know which kind of customer IDs are used by our users, and also we know which kind of identifiers are used as primary keys in our tables. So for each pair, or for each kind of translation we have to do, we are able to predefine the shortest path between those 2 kinds of identifiers. For example, if we need to translate a cell number into an email address, we know that the ISE is a neighbor of the cell number, and the email address is a neighbor of the ISE. But the email address is not a direct neighbor of the cell number. So we know that the shortest path for this kind of translation is via the ISE. We have developed a C++ library which offers an API for the graph exploration. And here is an example where we are looking for H, and we start from A. A has 4 neighbors, B, C, F, and G. C and G are not predefined in our shortest path, so we know that we don't need to explore them anymore. It remains only B and F. What is interesting here is that if we need to explore more than one vertex at a time, we can use the in operator in the where clause, and with only one query, we are able to explore all the neighbors of more than one vertex. Now, if we focus on B, B has 2 neighbors, A and D. A has already been explored in the previous step. D It's not predefined in the shortest path too, so we don't want to explore it anymore. It remains F to explore. F has 3 neighbors, A, G, and H. A has already been explored in the previous step. G has already been discarded in the previous step. It remains H, and H is what we were looking for. So what you have seen here is that with only 2 queries, we were able to retrieve what we were looking for. We were able to retrieve H, what we were looking for. It means that when we are looking for the direct neighbor, it requires only 1 select. When we are looking for the neighbor of a neighbor, it requires 2 select, and so on. We execute a few hundreds of searches per second. And even if we need to execute, if we have to execute a few queries for each search, we have a very low response time here. A response time for a search is between 2 milliseconds and 3.5 milliseconds. Here it is an example of on how we take benefit of from our Fusion IO cards, which give us very fast, very low response time for read queries. And also, we have developed this feature in C++, which is also very, very efficient. So my conclusion about this component is that Cassandra works very differently than a relational database. Probably the design that we were using with relational databases with a lot of secondary indexes could work, but here I think it was not the best design. And here, I think that what is very, very important is here that we favor the access to data through the partitioning key. And of course, accessing the data through the partitioning key is the most efficient path when we use Cassandra. And here, that's the reason why also we have a very low response time. And also, we have a linear scalability for this feature. That's all for carrying. So here, with carrying, what you have seen here is that we have a very good behavior with our application PNS, with Cassandra. Mainly when we use very, very simple queries. So you have seen that we have a response time for 3 milliseconds, even if we have to execute 2 or 3 queries. But now, we would like to do some analytics with the data stored in Cassandra. And for analytics, as you can imagine, we need to execute more complex queries. Usually, we want to call aggregate functions such as mean, max, average. We want to use the group by clause. So we need to scan tables. And with a Cassandra query language, it's not possible to call aggregate functions to use group by clause. So that's the reason why we have decided to use Hadoop Hive for doing analytics. And here, I would like to explain how we have installed Hadoop Hive in such a way that now, when we are running analytic queries, there is absolutely no impact in for our quality of service. At the end of the last year, our cluster was in 2 data centers, in Paris and in the French Riviera, with 16 nodes in each data center. We are using a replication factor of 3 in each data center. And we were using a consistency level of 1 or local quorum for our online queries. We have a pool of web servers in the data center 1. We have another pool of web servers in data center 2. And the requests from the web servers in data center 1 are sent to the Cassandra nodes in the data center 1, and the requests from the web servers in data center 2 are sent to the Cassandra nodes in data center 2. Because we want to run analytics, we have decided to add a third data center in our platform. Because we don't need a very high availability for analytics, we have decided to set a replication factor of 1 only in this third data center. So we need less storage space, and also we need less nodes. In data center 1 and data center 2, we are using Fusion IO cards, which give us very low response time for our online queries. For analytics, we have decided to use cheaper disks. So now we have a cluster like this. There is no change in data center 1 and data center 2. And you can see the third data center in orange with only 4 nodes. And we have installed also Cassandra in these 4 nodes in such a way that the Cassandra nodes belong to, the third data center belong to the same cluster as the nodes in data center 1 and data center 2. So when an update query is executed in data center 1 or data center 2, it is automatically replicated in the third data center. We have also installed Hadoop Hive in the 4 nodes in the third data center in such a way that the Hive queries are able to read directly the data in the Cassandra tables. And so now we are very happy because we are able to execute Hive queries. So we are able to call aggregate functions such as average, mean, and max with our Hive queries. We are able to use group by clause with our Hive queries. So we are very happy. We are very happy until we did the first bench with our Hive queries. And what happened when we did the first bench in our test platform? At first, what we have seen is that the 4 nodes in the third data center were very, very, very busy. There was a very high load average of CPU. The mapreduce tasks were taking quite all the memory. There were a lot of IO disks in the 4 nodes in the third data center. So what happened? There were a lot of timeouts for the online queries, for the online read queries in data center 1 and data center 2. The reason of that is that we were using consistency level 1. And when we are using this kind of consistency level, when a Cassandra node in data center 1 or data center 2 receive a read query with consistency level 1, this Cassandra node is the coordinator of the query and sends this query to one of the replica in the cluster. Sometimes this query was executed locally in the same data center, and sometimes this query was sent to another data center. And sometimes when this query was sent to data center 3, the node in data center 3 was too much busy and was not able to execute this query. That's the reason why we had some timeouts for our online read queries. With the update queries, there were also a lot of incidents. And it's quite the same problem. When a Cassandra node in data center 1 or data center 2 receives an update query, this node sends this update query to all the replica in the cluster. So the update was executed without any problem in data center 1 or data center 2. But the replica in data center 3 was too much busy and was not able to execute this update. So the problem is how to solve all those kind of errors. At first, the first thing we did is to use the right consistency level. When we began to work with Hive and Hadoop, we were using Cassandra 1.2.2. And with this version of Cassandra, the consistency level local 1 was not yet available. So we have upgraded our version, and now we are using Cassandra 1.2.13. And at first, we use the consistency level local 1 for the mapreduce tasks. So now we are sure that at first the mapreduce tasks are executed in the third data center, and only in this third data center, and the queries are never sent to data center 1 or data center 2. And of course, we have, for the online read queries now, we use the consistency level local 1 instead of using consistency level 1. So now we are sure that the online read queries are executed locally in data center 1 or data center 2 and are never sent to data center 3. And just with that, we have solved the problem for the timeouts of the read queries. But now we have still the problem with the hinted handoff for the update queries. At first, what we have decided is to use the cgroups. Cgroup is a Linux feature which can guarantee a minimum of resources for some Linux processes. And here, now we are using cgroups to guarantee a minimum of CPU and RAM for the Cassandra processes. We would like also to use cgroup to guarantee a minimum of I/O disk for our online queries. But here the problem is that the map task calls the Cassandra processes when reading data on disk. So we are not able to distinguish the I/O made for the online queries from the I/O made for the analytic queries. So we use cgroups only for guarantee a minimum of CPU and RAM for online queries. Second solution, we have decided to swap global read repairs and local read repairs. By default, with Cassandra 1.2, the parameter read repair chance is set to 0.1, and the parameter DC local read repair chance is set to 0.0. It means that when we execute 15,000 of queries per second, of requeries per second, 10% of these read queries generate a global read repair. It means that there are 1,500 read queries which are executed in the third data center, which makes a lot of, which makes some load in the nodes in the third data center and also some I/O disk. So here, just by swapping local and global read repairs, we were able to avoid the requeries from the read repairs in the third data center. And here it's very interesting because we have seen before in the previous slide that we were not able to guarantee a minimum of I/O disks for our online queries, but we are able to avoid them, some of them, so it's better. And now, in the latest version of Cassandra, the local read repair is now the default. There was also an interesting question. How many virtual nodes per Cassandra node in the third data center? Here the problem is that when we want to execute a mapreduce task, when we want to execute a Hive query, it generates some mapreduce task, and there is at least one map task per virtual node in the third data center. So if you have 256 virtual nodes per Cassandra node in the third data center, you will have at least 256 map tasks per node in the third data center, which is a lot. It's too much. And it's not very important. It's not efficient at all to have so much map tasks. The best solution here should be to disable the virtual nodes in the third data center. But if we do that, it means that if we want to add new nodes in our third data center, it's less easy because it's so easy to add new nodes now with your virtual nodes. So we have decided to use the virtual nodes in the third data center. So now when we want to add new nodes, it's easy to do. We don't have to redefine the tokens of each node and so on, as in the past, as in the first version of Cassandra. And according to our bench now, with 64 virtual nodes per node, it works correctly. It's not so efficient, but if we disable the virtual nodes, but it works, and for us, that's good. About the Hive handler that we are using in our platform, when we began to work with Hadoop and Hive, we were using the version Cassandra 1.2.2. And with this version, we found a few bugs in the Hive handler. So we have decided to fork this Hive handler. We have solved those bugs. We have also added the feature, which is the authentication. So now when we want to collect to Cassandra from Hive, we have to provide a login and password. The bugs that we have found in the Hive handler are solved now in the latest version of Cassandra. So, but if you want to use our handler, it is available in GitHub. And here I would like to thank my colleague Cyril Sedbon, who work on this handler. At Orange, we work with a Cloudera distribution of Hadoop, the 4.4 distribution, version 4.4, and we now the version 1.2.13 of Cassandra. So I know that this handler works with versions of Hadoop and Cassandra. We didn't did any test with other versions of Hadoop and Cassandra. My conclusion about Hadoop and Hive is that the installation was a little bit tricky. And here I didn't talk about the optimization of Hadoop and Hive. I talked just about the isolation between Hive and Cassandra. But if we want to do some analytics, we didn't have choice, because with the Cassandra query language, we are not able to call aggregate functions and so on. So here we had to rethink our architecture. And now, what is very interesting is that we are able to do analytics with Hadoop and Hive, but we have also a better isolation with Hive, between Hive and Cassandra. I remember that when we were using relational databases, we were running our queries, we are scanning tables, we are running our analytic queries in the same server than the online queries. So it was not very, very safe to do this kind of thing. And here, we had to rethink our architecture because it was not possible to do that. And now we have a better quality of service, a better behavior of our application. Another conclusion about this feature is that when we did that, we have also discovered a very, very interesting ecosystem around Cassandra. And for me, it's very interesting. I have discovered that Cassandra doesn't live alone. Cassandra has many friends around her, and with this ecosystem, we can work around many limitations of Cassandra, and I think here about the limitations of the query language, because as I said previously, this language doesn't allow to call aggregate functions. At Orange, we are also using some other Storm. We are using Zookeeper. We are using a few components of this ecosystem, and for us, now this ecosystem helps a lot too. My conclusion about the season 2 is that we had to rethink some of our components when we did the migration from relational databases to Cassandra. Because Cassandra doesn't work as a relational database. So it's very important to accept that. We had also to adapt our architecture, so we had added a third data center for that, for example. And thanks to Cassandra and this ecosystem, so we were able to leverage our application. And now PNS 3.0 for us is a real success, because now we have an application which works very, very well. We were able to do the migration of all the features that we are using with relational database. The migration is done now, and we have a better behavior with Cassandra and with the ecosystem. Thank you very much for your attention.